Hello, I welcome you all in the fluid mechanics lecture series. Today's topic is continuity equation. Continuity equation, there are two forms. One is conservation form and another is non-conservation. Conservation form, this is also called the Eulerian approach. And in a non-conservation form, this is also called the Lagrangian approach. In a Eulerian approach, what we consider a fluid element in a fixed point, right? This is not moving with the flow. Here, this is a fixed point. But in a Lagrangian approach, this fluid element is moving with the fluid flow, right? So, in the direction of flow, right? So, uh, when we drive the expression, so we will get the continuity equation this form, right? This is the continuity equation, right? So, when we drive for Lagrangian approach, so we will get the continuity equation in this form, right? So this is so so here we know this del rho by del t. This is we can write it this one. This is the total derivative of material derivative. This is also called this one. So this value we already know. No, this value equals to del rho by delta t plus uh, v dot del into rho, right? So we know this one. We- So here, so if there the derivation here the derivation of continuity equation, there are two method. One is the differential control volume method. When we drive this, so we will get this equation, and another is the integral method. Here we integrate the net mass stored within the control volume, right? Change the rate of change of mass within the control volume, and this is equals to the mass flux coming from the control surface. So when we convert this control surface into the control volume, so here divergence theorem is there. So with help of the divergence theorem, we can write it in this form, right? And this control volume, we take it out integration of this one. So this is equals to, so here it is dv, right? So dv this is equal to 0. So we will get same expression in a differential form and in a integral form also, right? But in a Lagrangian approach, here we are assume delta m is constant. That mass is constant. So when we different we dm, we can rewrite delta m. This is equal to density into volume. Here it is volume of the uh, this is the control volume, right? So we know when we expand it, uh, so we can rewrite when we expand it. So we first term we take as a constant and differentiate second term, and uh, second term we take as a constant first time. Mean differentiate by parts, right? So when we rearrange this one, so we can write this term first here, and then this term is here, and also rearrange it. So we can write it in this form. So this is called the divergence of velocity. So divergence of velocity, this is this is called divergence. This term, this is called divergence. In a previous lecture, we have already derived this one, right? So this is the divergence. So in a here there is conservation form and another is non-conservation form. In a conservation form, the fluid element at a constant at a fixed point, right? So we measure the flow property within this control volume. But in a non-conservative form, the fluid element is moving with fluid. This is called the Eulerian approach, and this is called the Lagrangian approach, right? So in a Cartesian coordinates, we can write it this one. So when in the vector form, when we write this in vector form, so we can write it. This is same equation in a vector form, or same equation in a index notation. If we use the index notation, so but different people are using the different notations. So but in a non-conservation form, here del rho by del t, this is we can write it this one, right? So when we uh, expand, when we put this value, so we will get this expression, right? So this is the, or in this is the in index notation form, right? So we can write this one, right? Okay. So next lecture, we will take some problem. Thank you very much.